Now consider dynamic programming. We first look at the flow chart for a deterministic system. We define a stage by S, a decision by U as before, a state variable as I, and a return as R. And we notice that we begin with some value of our state variable. We apply in stage 1 a control here, and out comes a result R1. That in turn determines all three of these, help to determine what the value of x2 will be for the second stage. And again, in stage 2, we choose a control variable, U2, we choose the decision to make, out comes a return, and we get the new state variable x3, and so on until we come to a terminal value here. Now, how do we solve a system like this? Well, dynamic programming uses a backward recursive method for solving problems numerically, beginning with the salvage value, which is given by S as a function of the terminal value, the state variable. Then in period t minus 1, we choose the decision variable at time t minus 1 that maximizes the current return, given by R as a function of the state and control variables at that time, plus the associated but discounted value of xt. In other words, the discounted salvage value of xt. We denote that value vt minus 1. So at vt minus 1, we can determine that through the choice of our decision variable ut minus 1, and we want to do that in such a way that we maximize the net return given by what the state variable is and what decision we apply, plus the discounted value of sxt, where beta, as before, is our discount factor given by 1 over 1 plus the discount rate. So then we back off to 2 years before the end of the time horizon, and now we choose a decision variable at time big T minus 2 to maximize the value function given by this expression down below. All right, in this case, we choose our decision at time big T minus 2 in such a way that it takes into account what our current return is going to be, plus the effect that our current decision has on what our future return will be. And this future return, v subscript big T minus 1, assumes that we've made the optimal choice, or that we will make the optimal decision in period big T minus 1. An example of the backward recursive approach is provided in the diagram below, where what we have is a automobile replacement problem. So in this last stage that we're looking at, stage 4, this refers to the last year that the person will own the car. So if we look at the last year, and if the person were to replace the car, it would cost them $6,000, and if they were to keep it, it would only cost $4,000 in terms of repair and that. And we take the minimum of that, and that turns out to be $4,000. Okay, then we do the same thing for this comparison, and we find that the minimum is $3,000, and finally for this comparison here, and we find that is $5,500. Now if we go back to stage 3, so this is the year before that we make the decision, the year before we make the final decision, we find that if we keep the car, we incur costs of $3,000 to go to stage 4, but at stage 4 we incur a cost of only $4,000, and that cost is due to keeping it for the year after. So that's your optimal decision in stage 4, which enters into the stage 3 decision. If we were to replace that car, it would cost us $4,500 plus $3,000, which is the minimum if we were to replace it, and then the optimal choice coming in stage 4, which would be to keep it. In fact, in stage 4, it's always optimal in this case to keep the car. So when we add those two numbers up, we get a number of $4,500 plus $3,000, which is $7,500, which is greater than if we were to keep the car. So in stage 3, if we come up that arm, we're going to keep it. So this is the decision here if we go that direction. If we come at it from the other direction, we have a replace, and it would cost $6,000 to replace, and then the optimal decision would be here, this one again. So it would be $6,000, which is the sum of $3,500 and $2,500, plus the $3,000, which would be $9,000 if we were to replace it. If we were to keep it, it would cost us $5,500 here, and this would be $4,000, so the cost would be $9,000 total. So in comparison, the cheaper decision is this one here. All right, to replace it if we end up in that. That's $6,000 plus $3,000 gives me $9,000. $4,000 plus $5,500 gives me $9,500. Now, if we go to stage 2, then we do the same kind of exercise. In fact, in stage 2, we find that it's optimal to replace the vehicle, all right, and rather than keep the vehicle, which is a higher cost decision. So this slide, I'll keep it on for a few seconds, basically describes what we did in the previous slides. And the final looks like this, where the red line indicates the optimal path that should be taken once we are making a decision in stage 1 to replace the car that we had at that time. Now, returning back to the foregoing procedure, we end up having a recursive relationship and a recursive equation, which is known as Bellman's equation. And it basically summarizes what we do over time. And what we do is we take the first order conditions. So in the first order condition that we find, we take the derivative of both sides with respect to the state variable. So that ends up being, in this equation here, the partial of the value at time t with respect to the state variable at t is equal to the derivative of the, or the partial of the return with respect to the state variable plus beta times the derivative of the value function, the future value, with respect to the state variable at the future time, multiplied by the partial of xt over partial of xt. So partial of xt plus 1, remember xt plus 1 is equal to, if we rearrange it, xt plus that function f, function of xt ut. So we take that derivative of xt with respect to little xt, pardon me, the derivative of xt plus 1 with respect to xt. The second condition is, again, your maximum principle, if you like, which says that the partial of the value function with respect to the choice variable is equal to the partial of the net return in the current period with respect to the choice variable plus the discounted value of the derivative of vt plus 1 with respect to xt plus 1 multiplied by the partial of xt plus 1 with respect to the choice variable ut, and we set that to 0. Now the important thing to note is that these values are Lagrange multipliers. Why? Because the Lagrange multiplier is simply the shadow price, which tells us what the increase in the objective function will be for a 1 unit increase in the constraints. Now when we take those two equations and we rearrange them, so we rewrite number 1 as lambda t is equal to the partial of the return with respect to xt plus beta lambda t plus 1 plus beta lambda t plus 1 times the partial of f with respect to xt. And we can rearrange that and we get this expression, which is the equation that we had identically when we talked about the Hamiltonian and the Lagrangian. And likewise, we can rewrite equation 2 in the same way and recover the same equations that we had from the discrete time Lagrangian and from the discrete time Hamiltonian. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.